My name is Ryan Spitler, and in this video, I wanted to give a little bit of background and some extra definitions, maybe some extra motivation for some of the things that were going on in my talk for about linear representations and finite quotients. So the groups that we're going to be interested in this background material and in the talk mostly are finitely generated groups. So we'll say gamma, some finitely generated group. We're interested in understanding the finite quotients of this group gamma. So one way to think about this is to collect sort of all of the finite quotient groups for gamma, and we'll denote this by C of gamma. And this is the set or maybe class, I don't know, of isomorphism classes of groups Q such that gamma surjects Q and the cardinality of Q is finite. So this is just supposed to be the collection of all isomorphism classes of finite quotients of gamma. One thing we can do with this collection of finite groups is we can sort of package it up into a tighter little deal that can be more useful. So what we'll package it into is called the profinite completion. We'll denote it with gamma hat. It's the inverse limit of the quotients, gamma mod n, where n is a normal subgroup of gamma and it's a finite index. So this is going to be some finite quotient group, and we're taking the inverse limit of this with a directed system that comes from sort of the reversed inclusion of these finite index subgroups. And a nice thing about this package, the profinite completion, is that it's a topological group. So it will have some natural topology on it coming from these surjections onto these finite sets. And it will be totally disconnected and compact. So it's a relatively nice topology. This can be a little weird to think about at first if you've never seen it before, so I thought I would give a nice specific example of a profinite group, the best kind of profinite group, in fact. So the p-adic integers is an example of a profinite group. That's what I'm going to use. Z sub p represents for me the profinite integers, mod p, the p-adic integers. And so this particular profinite group is the inverse limit of the finite groups Z mod p to the n. So you're taking the integers and you're just modding out by p raised to some power n. You let n vary, you have a natural sort of surjection from one to the next, and you take the inverse limit of this. So what is like an element of this inverse limit of this profinite group? Well, the way I usually think about them is that x in ZP, these elements of this profinite group are actually a subgroup of the direct product of all of these finite groups. So we have x is actually going to be an element in the direct product, x sub n, where we sort of index over n. We have z mod p squared, z mod p to the third. We have this direct product over all of these. And we choose some element, x sub n, from each of the z mod p to the n. And for it to, so it's this x is some subgroup, is some element in this direct product. And what's the condition that we want it to satisfy to be in this profinite group? Well, we need the choice of element to be coherent, sort of between each factor, meaning that if we have x sub n plus 1, meaning some element of z mod p to the n plus 1, when we reduce mod p to the n, sort of further reduce, we should get the chosen element of x sub n. So these are just the elements of the direct product of all of these things, which are coherent with respect to the maps between them. The topology, at least, roughly what should this topology look like? Well, we'll say that x and y, so if y is some other element in ZP, we'll say that y is close to x, and the degree of closeness depends on this when xn is equal to yn for all of the small n. So if you agree with x on all of the z mod p squared, z mod p to the third, you're going to be close to that x. Okay, so that's one nice profinite group. Another profinite group is z hat, the profinite completion of the integers. So what are all of the finite quotients of the integers? It's just z mod m, where you let m vary. So these are all of the finite cyclic groups. And when you have maps between them, you have a map from z mod m onto Z mod L exactly when L divides M. So like Z mod 6 surjects Z mod 3, but there's no map from Z mod 6 to Z mod 5. So that's sort of what that system looks like. And then it's a fact that you can show using like the Chinese remainder theorem or something like this, that if you take this full profinite completion of Z, that you get the product over all of the P of the ZP factors. So if you have any particular cyclic group, it splits up into a direct product of the sort of P primary factors. And that's what allows you to show this product decomposition. So there's a nice concrete example of a profinite group and a profinite completion. Okay, so one might wonder, what does this profinite completion actually detect? So this profinite completion is determined exactly by that class, that collection of all finite quotients, at least when gamma is finitely generated. So if you had some infinitely generated group, this could be a little tricky, but for finitely generated groups, the profinite completion essentially detects this, at least with its topology included, detects the collection of finite quotients. There is a map from gamma to its profinite completion. If you're thinking about the profinite completion as living in this direct product, all that this map is you take some element gamma in gamma, and you map it to the element of this direct product, which is exactly its reduction mod n at each of those factors. And this will give you a coherent choice of elements in that direct product, and so it will give an element in the profinite completion. And this map will be injective exactly when gamma is residually finite. So what does residually finite mean? It means that every element of gamma survives in some finite quotient, meaning that there will be some finite quotient of gamma where that element is non-trivial. And so when that happens, you will have at least one of your factors in this direct product, which is non-trivial, and so you'll be a non-trivial element. So usually we will assume almost always that the groups that we're thinking about are finitely generated and residually finite. One other nice property of the profinite completion is that it has a universal property, meaning that if I have any map from gamma, say we'll call the map F, to P, some profinite group, meaning some inverse topological group that comes from this inverse limit operation on a collection of finite groups. So if I have any map from gamma to any profinite group, it will actually extend through the profinite completion. So the profinite completion is sort of the universal profinite envelope or something of gamma, and it will extend uniquely. So for this map F from gamma to this profinite group P, there's a unique continuous map, which one might call F hat from the profinite completion to P, which extends F. So the kinds of questions then one often asks about these profinite completions and finite quotient sorts of things is, what can the profinite completion of gamma detect about gamma? So there's lots of results about this. In general, one can detect if a group is abelian from its profinite completion. You can detect if it's nilpotent, if it satisfies particular group laws. In other more restricted cases, there's other properties that one can see, but there's lots of properties for groups gamma that cannot be detected by its profinite completion. So you can find different groups with the same profinite completion where one has this property and one does not. From the title of my talk, you might think maybe there's something about linear representations that can be detected by the profinite completion, and we'll see some answers to that in the actual talk. And the best answer to like what can the profinite completion detect about gamma, maybe the best answer you could get is like it can actually determine gamma. So one can ask, can gamma hat determine gamma? Can the profinite completion determine gamma? Like up to isomorphism, it's the only group. Gamma is the only group with that as its profinite completion. So can this happen? And when this does happen, say if it did happen, we would say that that group gamma is profinitely rigid. And sometimes, to be very clear about what kind of profinite rigidity we mean, we would say that it's absolutely profinitely rigid. And what does that mean? That means if any mystery group lambda, which is finitely generated and residually finite, that's sort of a hidden intrinsic assumption that we're always making. Any residually finite, finitely generated group lambda with lambda having the same profinite completion as gamma will actually be isomorphic to gamma as abstract groups, as finitely generated groups. So this is what we'll call it if a group is completely determined by its profinite completion. This happens sometimes. It's easy to see for, it's easy-ish to see for like finitely generated abelian groups, but there's also some not so difficult examples of groups which are not profinitely rigid. And the question in general of determining if a group is profinitely rigid or not, when are groups profinitely rigid, when are they determined by their profinite completion is very challenging. Even the question of whether a free group, a non-abelian free group, is profinitely rigid is probably the biggest open question in this sort of research field. So we can't even answer it for the free group, which might hint that it's a little tricky at times. So this is an absolute profinite rigidity question, saying if I have some random, completely random group lambda, which happens to be finitely generated and residually finite, if it has the same profinite completion, then it has to be isomorphic to gamma. But you could ask similar questions, which are more relative, sort of saying that, okay, I'm not going to let lambda be any crazy group. Maybe it'll just be some like three-manifold group, or maybe it'll be a surface, like a surface group or a limit group. It'll come from some sort of restricted class of kinds of groups that I actually understand and can say something about. And there are lots of very important good results that answer these kinds of questions as well. So these relative profinite rigidity results are very important as well, but the absolute one is the one that I'll mostly talk about today. Okay, so that maybe concludes the motivation and some of the definitions or the background sorts of definitions. Then there's some specific things that I use in my talk, in my main talk, I guess, that I wanted to be sure everyone was clear about what are the definitions. So the first one I wanted to define is PSL2R. So we're starting out here. We're just going to have R being any ring. So usually by that, I'll mean commutative and with an identity element. And what am I going to start with? SL2R. This is the collection of 2x2 matrices whose coefficients come from R and who have determinant 1. And then PSL2R will be the quotient of this SL2R by the center, which in this case will be positive and negative, the identity. So this is what PSL2R, in case you've forgotten some of your classical matrix groups, this is what I mean when I say PSL2 of something. Let's see. So in particular, PSL2C, so C is a ring. It's a nice big field that's useful for many things. PSL2C is an algebraic group. It can be defined using certain equations. It's the collection of all solutions to a certain collection of equations, and it has a group structure that's sort of coherent with respect to this variety structure. What we'll say is that a subgroup of PSL2C is Zariski dense. What this usually means is that there's no sort of smaller collection of equations that all of the elements of gamma sort of simultaneously satisfy, that lives inside as sort of a proper subgroup. So we'll say that this is Zariski dense. There's an easier thing to say in this particular example. An easier thing to check is that gamma is not finite, and gamma is not conjugate into upper triangular matrices. So as long as you have a subgroup gamma of PSL2C, it's not finite, it's not conjugate into upper triangular matrices with this 0 down at the bottom, then it's Zariski dense. So that's what Zariski dense will mean for me and what it can mean for you today. So some important things here with respect to PSL2C, if we have M3 representing a hyperbolic 3 manifold, then M can be thought of as H3, the hyperbolic 3 space, modulo gamma, where gamma is the fundamental group of M, and gamma has a sort of particular representation into PSL2C. So gamma is sort of living inside of PSL2C in a special way, coming from this hyperbolic structure on M3, on the space. So how do you think about this PSL2C? How is it related to hyperbolic 3 space? Well, I'll give just a tiny answer. One way that I think about it is that H3, this hyperbolic 3 space, and sort of the disk model, well, okay, the disk model would be for 2-dimensional hyperbolic space, the ball model for 3-dimensional hyperbolic space. You can think about this 3-dimensional ball as living inside the interior of the Riemann sphere. So remember from complex analysis, the Riemann sphere is all of the complex numbers in addition to a point at infinity. You can think about this ball of the complex numbers and then the point at infinity as sort of so this sphere, the Riemann sphere, sort of surrounding the interior of the sphere, and thinking of the interior of that ball as the hyperbolic 3 space. And okay, what's nice about PSL2C? PSL2C acts as linear fractional transformations on the Riemann sphere. So PSL2C has a nice coherent action on the boundary of this 3 space, and then it sort of descends into the interior of the hyperbolic 3 space. But on the boundary, you can understand the action by the usual linear fractional transformations, where A, B, C, D maps the complex point Z to this fraction. Oh yes, and here's a nice little ball for that. Maybe I didn't need to be gesturing with my hands, but so this is sort of representing the Riemann sphere, 0, 1, -1, I, negative I, and infinity up here at the top. And then hyperbolic 3 space can sort of be thought of as being on the inside. Okay, so that's that. One last thing, I want to give a little bit of number theory definitions here as well. So I gave the definition of what is ZP, or I sort of tried to explain what are the p-adic integers. I showed that it's a p-adic group, but also this p-adic group structure also has a ring structure that you can put on it. Z mod p is a group, but it's also a ring. Z mod p squared is also a ring. So, so this whole profinite group is also a profinite ring. It has a natural multiplication structure on it. So ZP contains a lot of the rational numbers. It's an integral domain. Most of the rational numbers live inside there. The one number, or the one important number that doesn't live inside ZP, is 1 over P. There's sort of no place for 1 over P to live inside Z mod P or Z mod P squared, any of these. So if you add in this one extra number, 1 over P, you get all of the, and take the ring, you get all of Q. And if you take ZP, the p-adic integers, and add in 1 over P, you get QP, the p-adic numbers. And so now this is a field. Going from ZP, which is a compact, totally disconnected topological ring, we add in 1 over P, we lose compactness, but we still have local compactness. So QP is a locally compact topological field. There's another way to think of QP. It's also the completion of Q under a certain metric, which is very related to the sort of topology that we were talking about for ZP. This metric on Q is one where it measures high powers of P to be very small, very close to 0, and like high negative powers of P, so 1 over P to the n becomes very, very large. And you can figure out the rest for yourself maybe at some point. But what's important for us here is that this QP allows us, so this is involved in the definition of a place. So one of these p-adic metrics, so if you take a particular p-adic metric on Q and think about the completion of Q with respect to this metric, that can be called sometimes a finite place of Q. So one of these metrics, also related to valuations on the field, as well as the completion. These are sort of often called the places of Q, finite places of Q. And then the thing that I want to sort of say that generalizes that is there's something similar for any number field. So if K is any number field, meaning a finite quotient, a finite extension of Q, some finite field extension, K will have a finite place V and a completion KV for any of its prime ideals in its ring of integers. So how should one think of this related back here? Well, ZP, where did the P come from? P is a prime. This is related to the prime ideals in the ring Z. If you take this number field, you can look at its ring of integers, O sub K, look for its prime ideals. And then for each of these prime ideals, you can get a similar sort of metric on the field K. And if you take the completion of K with respect to that metric, you'll get KV, which again will be one of these locally compact topological fields. And the point of bringing up all of this is that these p-adic fields, and especially representations in these p-adic fields, are really the ones that we're interested in when we're trying to the ones that I'm interested in when we're trying to look at what can the profinite completion say about linear representations.